Welcome back, my friend. Tonight, we're going to journey through the strangest riddles the cosmos has ever posed. Paradoxes so deep that even our best scientists are still searching for answers. So get comfortable, let the stars be your ceiling, and the quiet hum of the universe guide you into rest. Let's begin. Chapter 1. Why the Night Sky is Dark. Olbers Paradox. If you've ever stood beneath a clear rural sky, far from artificial lights and city glow, you've probably noticed how overwhelmingly dark the night feels. Yes, stars are present, even galaxies, nebulae, and planets for those who know where to look, but the overwhelming impression is one of blackness. The vast majority of the sky is empty to the eye, and while this feels natural and even poetic, it presents a scientific mystery that puzzled astronomers for centuries. Why is the night sky dark? This question is the heart of what's known as Olbers' paradox, a deceptively simple problem that exposes deep truths about the structure and history of the cosmos. It's named after the German astronomer Heinrich Wilhelm Olbers, who formally described it in 1823. However, versions of the paradox had been recognized earlier. In the 17th century, Johannes Kepler raised a similar concern, suggesting that a truly infinite and eternal universe filled uniformly with stars should be filled with light. So much light, in fact, that the sky would be as bright as the surface of the sun in every direction. Let's examine why this idea seems reasonable at first glance. Imagine the universe as infinite and static, with stars distributed uniformly through all of space. Wherever you look, in any direction, your line of sight should eventually intersect the surface of a star, just as looking through a dense forest will eventually bring a tree trunk into view. And while the intensity of light decreases with distance due to the inverse square law, the number of stars in each concentric shell of space increases with the square of the radius. So the light received from each layer of stars, despite being farther away, should be roughly constant. Add up infinitely many layers of stars, and you'd expect a sky blazing with brilliance, not veiled in darkness. But the real night sky contradicts that expectation. It is mostly dark. Bright points of light are the exception, not the rule. This is the paradox. Under classical assumptions, the night sky shouldn't be dark, and yet it is. Early thinkers proposed several explanations, most of which turned out to be incomplete or incorrect. One of the most intuitive was the idea that dust and gas between stars block their light. But while interstellar material does absorb light, it doesn't provide a lasting solution. Any matter that absorbs light also heats up. Over long periods of time, that heated dust would re-radiate the energy as thermal emission. Eventually, the dust would glow just as brightly as the stars it obscures, and the night sky would again become luminous. This explanation violates the principle of thermodynamic equilibrium. Unless a mechanism constantly removes energy from the system, the darkness wouldn't last. Another idea involved non-uniform distribution of stars. Perhaps stars are not evenly spaced, and their density decreases at larger distances. But this doesn't help much in an infinite universe. Even if stars become sparse, the increase in volume of space at greater distances would still mean more stars exist in those outer regions. As you move farther out, you're looking through more space, and the total light received would still diverge toward infinity. Unless space itself is finite in volume, this alone doesn't solve the paradox. The resolution came only with the rise of modern cosmology in the 20th century. Specifically, with the understanding that the universe is not eternal, not static, and not infinite in what we can observe. First, the universe has a finite age. Based on observations of cosmic expansion, the Big Bang model tells us that the universe began approximately 13.8 billion years ago. This means we can only observe as far as light has had time to travel since that moment. The universe may be spatially infinite, but it is temporally bounded, and so is our observable region of it. Light takes time to travel. We cannot see objects whose light hasn't reached us yet. The limit of how far we can see defines the cosmic light horizon, roughly 46 billion light years in every direction, due to the stretching of space over time. Anything beyond this horizon is invisible, not because it isn't there, but because its photons have not had time to arrive. That instantly eliminates an infinite number of stars from our view. The sky is not filled with their light simply because that light is still in transit, possibly forever beyond our reach. But that's not the only reason for the darkness. The expansion of the universe introduces a second key effect, cosmological redshift. As space itself expands, it stretches the light traveling through it. This stretching increases the wavelength of the photons, reducing their energy. Light that was once visible can be shifted into the infrared, microwave, or even radio part of the spectrum. From our point of view, that light becomes too faint or too low in frequency to detect with the naked eye. This redshift is why the cosmic microwave background, CMB, exists. The CMB is the afterglow of the hot, dense early universe, released about 380,000 years after the Big Bang, when atoms first formed and space became transparent. Originally emitted in the visible and ultraviolet ranges, this radiation has been redshifted over billions of years into microwaves, now detectable only with special instruments. It is present everywhere in the sky, but not in a form we can see unaided. Additionally, as the universe expands, not only is the light from distant sources redshifted, but its intensity decreases due to dilution. The density of photons in expanding space drops. Distant galaxies contribute progressively less light, even before they're fully redshifted out of visibility. This makes the collective brightness of the universe far dimmer than what a static eternal model would predict. Another factor to consider is the limited lifespan of stars. Stars are not permanent fixtures. Their formation began a few 100 million years after the Big Bang, and even the most long-lived stars will eventually burn out. Many stars that formed early in cosmic history are now extinct. They no longer emit light, and their contribution to sky brightness has ceased. Stellar birth and death are ongoing processes, but they exist within cosmic limits. There are only so many stars at any given time, and they only shine for so long. Beyond this, observational astronomy confirms that even the combined light from all visible galaxies, observed through deep field images like those from the Hubble Space Telescope, contributes only a small fraction of the brightness needed to light up the sky. The Hubble Ultra Deep Field, one of the most sensitive images ever taken, captured thousands of galaxies in a tiny patch of sky. But the cumulative brightness of these galaxies, extrapolated across the entire sky, still accounts for only a faint glow, not anything close to a fully illuminated dome. And yet, the paradox continues to be useful, not because it's unresolved, but because it touches on so many critical aspects of cosmology. Solving it required abandoning the idea of a steady-state universe. It required introducing the concept of cosmic expansion, the finite age of the universe, the propagation limits of light, and the thermal history of space-time. It forced astronomers and physicists to think not just about what is visible, but about what is possible to be visible. The darkness of the night sky is, in a way, a direct confirmation of the Big Bang model. If the universe were infinite and unchanging, the sky would not be dark. The fact that it offers us a window into the origin, structure, and future of the cosmos. And yet, despite all that science has revealed, the emotional impact of the dark sky remains. You can understand the physics, trace the equations, and still feel the quiet awe of space pressing outward in every direction. The darkness isn't empty, it's just unreachable. It's a silence full of motion, a canvas shaped not only by the stars that shine, but by the ones too far, too old, or too stretched out to ever be seen again. When you look up, you're not just looking into space. You're looking into time, into a history written in light and a future hidden by distance. The darkness between the stars reminds us not just of how far we've come in understanding the universe, but how much remains beyond even the longest gaze. Chapter 2. The Uniformity of the Cosmos, the Horizon Problem. When we peer into the depths of the cosmos, we are met not by chaos, but by order. No matter where we look, the universe appears smooth and consistent. The arrangement of galaxies, the density of matter, and the temperature of background radiation all reflect a calm, large-scale uniformity that seems almost deliberate. This sameness is not just an aesthetic observation. It is something measurable, quantifiable, and deeply rooted in data. And yet, this very uniformity presents one of the most puzzling paradoxes in astrophysics. Why does the universe look so evenly spread out when distant regions should never have had time to agree on anything at all? This is the essence of what physicists call the horizon problem, and it becomes particularly stark when we examine the oldest light in the universe, the cosmic microwave background radiation. This faint glow, discovered by accident in the 1960s, comes from a time when the universe was just a few 100,000 years old. At that time, the cosmos had cooled enough for neutral atoms to form, allowing light to travel freely through space for the first time. That light, stretched and softened over billions of years by the expansion of the universe, still surrounds us today, forming a kind of all-sky thermal map of the early cosmos. When this radiation is measured with sensitive instruments, it reveals an astonishing fact. Its temperature is almost exactly the same in every direction. Even points on opposite sides of the sky, which are now separated by more than 90 billion light-years, differ in temperature by less than 1 part in 100,000. To scientists, this is more than surprising. It's suspicious, because according to standard Big Bang physics, those regions of the sky have never been in contact. There has never been enough time, even since the beginning of the universe, for light or any form of energy to travel from one side to the other. And if they've never communicated, how could they have reached the same temperature? How could they have agreed on their conditions? This contradiction, that disconnected parts of the universe appear thermally balanced, creates the horizon problem. In everyday physics, systems only come into equilibrium when they are able to interact. A cup of hot coffee cools because it exchanges heat with the surrounding air. Two distant systems without communication or energy transfer should evolve independently. And yet, cosmological observations say otherwise. The roots of this problem stretch back to the early formulations of the Big Bang theory itself. In the 1920s, astronomers like Edwin Hubble found that galaxies were receding from us, implying that space itself was expanding. Working backwards, this suggested a hot, dense origin for the universe. Over the next few decades, scientists developed a model in which the universe began in a singular explosion of space and time, cooling as it expanded. This theory successfully explained many phenomena: the abundance of light elements like helium, the redshift of galaxies, and eventually, the existence of the cosmic microwave background itself. But as measurements became more precise in the latter half of the 20th century, cracks began to appear. The smoothness of the microwave background couldn't be explained by any standard Big Bang scenario. In this traditional view, the universe simply expanded at a steady rate from its origin. But that didn't give time for distant regions to synchronize. The size of the observable universe, the portion of the cosmos from which light has had time to reach us, is limited. And back when the microwave background was released, that observable volume was much smaller. It should have broken into many disconnected regions, each evolving on its own. But it didn't. To fix this, cosmologists proposed a radical solution in the early 1980s: cosmic inflation. This idea, first introduced by physicist Alan Guth and further refined by others, suggested that the universe did not begin expanding smoothly. Instead, in its earliest moments, a sliver of a second after its birth, space underwent an extraordinary burst of accelerated expansion. During this period, the size of the universe grew exponentially, blowing up from a tiny subatomic patch into something orders of magnitude larger. This sudden expansion, though brief, changed everything. Before inflation occurred, the universe was small enough that all parts could exchange energy freely. It was a single, causally connected domain. Everything was in contact, and thermal equilibrium was possible. But once inflation began, this small, smooth region was stretched far beyond its original scale. Areas that were once neighbors became separated by vast distances, far beyond each other's horizons. And yet, because they had once been in equilibrium, they retained the same physical conditions. What we now see as distant parts of the sky were once side by side. Inflation doesn't just resolve the horizon problem, it also explains several other cosmological puzzles. It accounts for why the universe appears flat and not curved, why there are no observable magnetic monopoles, and where the seeds of structure, the tiny fluctuations in density that would grow into galaxies, originated. According to inflationary theory, quantum fluctuations in the early universe were amplified by the rapid expansion, turning microscopic randomness into macroscopic variation. These tiny differences became the initial blueprint for all structure in the cosmos. Yet inflation itself raises new questions. What caused it to start? What triggered it to stop? The mechanism often invoked involves a hypothetical energy field called the inflaton, which dominated the energy density of the universe during inflation and then decayed into regular matter and radiation. But this inflaton has not been observed, and its properties remain speculative. Furthermore, some versions of inflation suggest that it may be eternal, that new regions of space are still inflating beyond our view, creating a vast landscape of bubble universes with different physical properties. This leads naturally to the idea of a multiverse, in which our observable universe is just one small patch among countless others. Some researchers have proposed alternatives to inflation, aiming to explain the horizon problem through other mechanisms. One such idea is that the speed of light may have been much higher in the early universe. If true, this would allow distant regions to exchange energy and information quickly enough to reach equilibrium before the emission of the cosmic microwave background. Another proposal is that space and time themselves behave differently at extremely high energies. That the early universe operated under different physical laws which allowed for faster thermalization or non-local interactions. These ideas are less developed than inflation, but highlight the ongoing search for deeper understanding. One of the striking features of the horizon problem is how it takes a seemingly simple observation, the uniformity of the sky, and shows that it demands a profound explanation. That something so subtle and elegant requires a fundamental revision to our understanding of physics is a testament to the power of cosmological reasoning. The problem isn't merely that we don't know why the sky is so even. It's that, under ordinary physics, it shouldn't be even at all. Historically, this issue reflects a broader shift in how humans have come to understand the universe. Before the 20th century, the cosmos was often seen as eternal and unchanging. Then came the Big Bang, the expanding universe, and the realization that space itself had a history. Inflation and the horizon problem that gave rise to it represent a further evolution in this thinking, the idea that even the structure of causality itself can evolve, that space can stretch faster than light can travel, and that what we see today was shaped by a hidden past we cannot directly observe. The horizon problem remains one of cosmology's most illuminating questions, not because we don't have answers, but because in answering it, we've discovered entirely new layers of reality. It pushed physics beyond the boundaries of classical intuition and forced us to consider events that took place in less than a blink of an eye, moments that determined the fate of galaxies, stars, and life itself. And as always, when we look up at the sky, it's hard not to feel something more than curiosity. That the entire observable universe may have once been a single, connected point, a place where everything touched everything else, carries with it a quiet resonance. We are surrounded by light from a time when the cosmos was young, still smoothing itself out, still finding its balance. And in that light, stretched thin by billions of years, we find a story of togetherness, expansion, and the strange simplicity that lies beneath the infinite. Chapter 3. The Perfect Balance of Space. The Flatness Problem. When we think of the universe, we might imagine it as an infinite stretch of stars and galaxies curving through the dark, or perhaps as a sphere expanding outward into some undefined beyond. But in physics, the shape of the universe is not just a matter of imagery or metaphor. It is a measurable property defined by the geometry of space-time itself. And remarkably, when cosmologists have attempted to measure the geometry of the cosmos, they have discovered something so finely tuned, so delicately balanced, that it challenges our very understanding of how the universe came to be. This brings us to what is known as the flatness problem, one of the key puzzles in modern cosmology. At its core, the flatness problem asks why the universe appears so geometrically flat, and why that flatness has persisted over billions of years. It is not a philosophical question. It is one that arises directly from Einstein's theory of general relativity, which tells us that the geometry of the universe depends on its overall energy content. In general relativity, space can have one of three possible curvatures: positive, negative, or flat. A universe with positive curvature resembles the surface of a sphere, closed and finite, with parallel lines eventually converging. A universe with negative curvature is like a saddle, open and infinite, with parallel lines diverging. And a flat universe has Euclidean geometry. Parallel lines stay parallel, triangles have angles that sum to 180 degrees, and space neither curves inward nor outward. Which of these geometries our universe follows depends on its density, specifically, how the total energy density compares to a certain critical value. If the actual density is greater than this critical threshold, the universe curves positively. If it's less, the universe curves negatively. If the energy density is exactly equal to the critical value, the universe is flat. In the language of cosmology, this is described by the density parameter, denoted omega. When omega equals 1, the universe is perfectly flat. Measurements of the cosmic microwave background radiation and large-scale structure surveys have shown that our universe's omega is extremely close to 1, with any deviation too small to currently detect. In other words, space appears to be flat to within a tiny margin of error. The cosmos, on the largest scales, behaves as though its geometry is not curved at all. This observation is not controversial. It is backed by multiple independent lines of evidence. The question is why? The problem arises because flatness is unstable in the standard Big Bang model. If the universe started out with even the slightest curvature, just a tiny deviation from flatness, that deviation should have grown over time. In a decelerating universe, any small initial curvature becomes magnified. The analogy often used is balancing a pencil on its tip. In principle, it's possible, but in practice, the slightest nudge will send it falling. The same is true with the curvature of the universe. Unless omega was exactly 1 from the very beginning, the universe today should either be wildly curved or should have already collapsed long ago. The fact that omega is still so close to 1 means it must have started extraordinarily close to 1 in the first moments after the Big Bang. Just how precise are we talking? According to calculations in the early universe, say, within the first few seconds, omega would have needed to differ from 1 by no more than 1 part in 100 trillion. Any larger deviation would have led the universe to rapidly deviate from flatness. So the flatness problem is not just that the universe is flat now, but that it had to be so incredibly flat from the very beginning to still appear flat today. This seems like a huge coincidence, an unexplained fine-tuning of initial conditions. Why would the universe begin in such a delicately balanced state? The standard Big Bang theory by itself offers no mechanism to enforce this. It simply takes the flatness as a given, part of the initial conditions. But scientists are rarely content with unexplained precision. When a theory requires inputs that are so narrowly constrained, it raises suspicion. It suggests that something deeper is missing, some mechanism or principle that naturally sets the parameters instead of arbitrarily assuming them. This is where cosmic inflation, once again, enters the picture. Not as a solution to a single mystery, but as a broader explanatory framework. Inflation proposes that in the early universe, space expanded exponentially in an extremely short amount of time. This rapid expansion didn't just stretch out regions of space, it also flattened them. The effect of inflation on curvature is similar to the effect of zooming in on a curved surface. Imagine standing on a balloon. From a distance, its roundness is obvious. But if the balloon were suddenly expanded 1,000 times in size, your local patch would appear almost perfectly flat. The curvature would still exist globally, but within your observational range, it would be indistinguishable from flatness. Inflation, by massively enlarging the universe, smoothed out any original curvature, driving omega toward 1 regardless of where it started. This means that even if the universe began with a slightly curved geometry, inflation would have flattened it to extraordinary precision. It would explain why the universe looks flat today without requiring perfect initial conditions. Flatness becomes not a coincidence, but a consequence of early dynamics. Inflation turns the unstable pencil into a table, wide, stable, and resistant to tipping. It offers a natural explanation for what would otherwise appear to be an improbable fine-tuning. But just as inflation elegantly resolves the flatness problem, it also raises new and challenging questions. What caused the inflationary expansion? What field or force drove it? And what determined when it stopped? While many models exist, often involving hypothetical scalar fields and potential energy landscapes, none have been definitively confirmed. The theory, though powerful, remains incomplete. Furthermore, inflation is not the only possible solution to the flatness problem. Some alternative theories modify gravity itself or introduce new forms of matter and energy that could influence the evolution of curvature. Others suggest that the geometry of the universe may emerge from deeper quantum principles, perhaps as a statistical average or a holographic projection of more fundamental dimensions. These ideas remain speculative, but highlight the rich frontier of modern cosmology, where geometry, quantum physics, and thermodynamics converge. Interestingly, some physicists have considered whether the universe's apparent flatness might not be a coincidence, but a requirement for the emergence of observers like us. In a strongly curved universe, whether positively or negatively, the formation of stable galaxies and planetary systems might be more difficult or even impossible. A flat or nearly flat universe may be the only kind in which complex structure can persist long enough for life to evolve. This line of reasoning is part of the broader anthropic principle, the idea that the universe must allow for observers because we are here to observe it. While not a satisfying physical explanation on its own, it provides a possible context in which to interpret fine-tuning. Historically, the search for the shape of the universe has always been tied to deeper philosophical questions. In ancient times, thinkers imagined the heavens as perfect spheres or infinite voids. As telescopes advanced, astronomers sought evidence for curvature in the arrangement of stars and galaxies. But it wasn't until the 20th century, with the advent of general relativity, that curvature became a physical quantity, tied directly to matter and energy. Today, the best data we have shows that the universe is flat to within a fraction of a percent. But even that measurement is limited by the size of our observable horizon. It is still possible that the universe is slightly curved on scales beyond what we can see. It might be open or closed in a way that only becomes evident at distances forever beyond our reach. In this sense, the flatness problem is not just about geometry, but about limits, the limits of observation, of inference, and of what it means to know the shape of something infinite. And so the question remains, is the flatness of the universe a fortunate accident, a relic of some deeper law, or the result of cosmic inflation? The data leans toward inflation, but the story is not yet finished. Each new measurement of background radiation, of gravitational waves, of galaxy distributions brings us closer. But the ultimate cause of cosmic flatness may still lie ahead of us, hidden in equations we haven't yet written. And yet there's something quietly humbling about it all. To live in a universe so balanced, so finely tuned that space itself neither bends nor warps, that it stretches out with perfect evenness in every direction, is a reminder of the strange precision underlying existence. We are not adrift in a jagged or chaotic world. We are held by symmetry, by geometry, by a silent, invisible equilibrium that makes structure, time, and even thought possible. Somewhere in that balance, you exist, not by accident, but as part of a space that was smooth enough to expand, flat enough to last, and quiet enough to evolve. Chapter 4. The Missing Antimatter, Baryon Asymmetry. The known universe is made almost entirely of matter. Every planet, star, cloud, and galaxy is composed of atoms made of protons, neutrons, and electrons. From the smallest grain of dust to the largest galaxy cluster, the visible cosmos appears to follow this rule with striking consistency. Matter dominates. And yet, this overwhelming prevalence of matter is one of the deepest and most unsettling mysteries in cosmology and particle physics. According to the most well-tested physical theories, matter should not dominate at all. The laws that govern particle interactions, including the behavior of energy, fields, and fundamental forces, suggest that the universe should have created equal amounts of matter and antimatter during its earliest moments. That is, for every proton, there should have been an antiproton, for every electron, a positron, and for every neutron, an antineutron. But this is clearly not what we observe. The antimatter is gone. What remains is a tiny excess of matter, just enough to build the entire visible universe, and a lingering question: where did all the antimatter go? This discrepancy is known as the Baryon asymmetry of the universe, named after the class of particles, baryons, which includes protons and neutrons, that make up the bulk of normal matter. While there is evidence that antimatter exists in rare forms and in controlled laboratory conditions, the cosmos at large appears to be devoid of any significant concentrations of it. When particles of matter and antimatter meet, they annihilate one another in a burst of pure energy, converting their mass into high-energy photons. If the universe had been perfectly symmetric, all the matter and antimatter would have annihilated shortly after the Big Bang, leaving behind only radiation. But clearly, that didn't happen. Instead, a small excess of matter, perhaps just one particle of matter for every billion particles of antimatter, must have existed. This tiny imbalance was all that remained after the rest annihilated. That small leftover became the entire material content of the universe. This imbalance is at the heart of the Baryon asymmetry problem. How did the early universe generate such a preference for matter over antimatter? The fundamental laws of physics are, in most respects, symmetric between matter and antimatter. The equations describing the interactions of particles in quantum field theory do not intrinsically favor one over the other. Charge, parity, and time reversal, collectively known as CPT symmetry, hold as a core feature of these interactions. And yet, there must be some mechanism that broke this symmetry early in cosmic history. The idea that the symmetry between matter and antimatter must have been broken is not just philosophical. It has been given rigorous theoretical treatment. In the 1960s, the Russian physicist Andrei Sakharov proposed 3 conditions, now known as the Sakharov conditions, that are necessary to produce an excess of matter in the early universe. First, baryon number violation must occur, meaning that interactions must exist that can change the total number of baryons in the universe. Second, there must be a violation of C and CP symmetry, so that reactions produce more matter than antimatter. Third, the process must occur in a setting that is out of thermal equilibrium, which is essential because in equilibrium, detailed balance would undo any net baryon production. Each of these conditions is deeply rooted in particle physics, and their possible fulfillment has been explored in various theoretical models. One of the earliest and most studied frameworks is based on grand unified theories, or GUTs. These theories attempt to unify the strong, weak, and electromagnetic forces into a single framework, operating at extremely high energies. In many GUT models, interactions that violate baryon number naturally arise, allowing for processes in which baryons can be created or destroyed. Moreover, these theories often predict the existence of heavy particles, X and Y bosons, that can decay into both matter and antimatter, but in slightly unequal proportions if CP symmetry is violated. This decay asymmetry would, in principle, favor the production of matter over antimatter by a tiny amount. As the universe cooled and these heavy particles decayed, the imbalance would become frozen into the fabric of the cosmos, resulting in the matter-dominated universe we observe today. While this explanation is conceptually sound, it remains hypothetical. The predicted particles have never been observed, and the unification energies involved are many orders of magnitude beyond what current particle accelerators can probe. Another candidate mechanism for generating baryon asymmetry is known as leptogenesis, which focuses on leptons, a class of particles that includes electrons and neutrinos. In this scenario, heavy right-handed neutrinos predicted by certain extensions of the standard model of particle physics decay in ways that violate lepton number and CP symmetry. These decays would produce an excess of leptons over antileptons. Later, through interactions involving the electroweak force, this lepton asymmetry could be converted into a baryon asymmetry via processes known as Phaleron transitions. Leptogenesis has the appeal of being connected to the observed tiny masses of neutrinos, which may themselves point to physics beyond the standard model. Despite the elegance of these ideas, they remain unconfirmed. The difficulty lies not in the conceptual framework, but in the inaccessibility of the energy scales involved. The processes that would have generated the matter-antimatter asymmetry occurred at energies that prevailed less than a trillionth of a second after the Big Bang. Our current experimental tools are powerful, the Large Hadron Collider being the most advanced, but they cannot yet reach the energy regimes where baryogenesis likely took place. And so, the problem remains open. Adding complexity to the mystery is the fact that we don't observe large regions of antimatter anywhere in the visible universe. If the universe were composed of large domains of matter and antimatter, separated by vast distances, we might expect to observe annihilation at the boundaries, areas where matter and antimatter regions meet. Such annihilations would produce telltale gamma-ray signatures. However, surveys of gamma-ray background radiation and detailed cosmic observations have revealed no such evidence. The entire visible universe seems to be made of matter alone. This homogeneity strongly supports the idea that the asymmetry was generated very early in the universe's history, long before the formation of galaxies or large-scale structures. Whatever process created the imbalance did so uniformly across the entire observable region of space. This raises another question. Is the matter-dominated universe we observe just a local feature? Could there be regions beyond our horizon, far across the unobservable universe, where antimatter dominates instead? In principle, this is not ruled out, but without observational evidence, it remains speculative. The baryon asymmetry is not just a curious imbalance. It is an essential condition for the existence of structure, chemistry, planets, and life. If the matter and antimatter had been produced in equal quantities and had annihilated completely, the universe would be filled only with radiation, a vast bath of photons with no atoms to form stars or organisms. The asymmetry, though tiny in magnitude, was decisive in determining the future evolution of the cosmos. Yet, this fact also deepens the mystery. Why should there have been just enough matter to escape annihilation? Why not more? Why not less? The parameters required for a habitable universe seem, again, to be finely tuned. The balance between the initial conditions, the laws of particle physics, and the dynamical processes of the early universe must have aligned with extraordinary precision to yield the world we now inhabit. The pursuit of answers continues. Experiments at particle accelerators search for signs of CP violation beyond what has been observed in the behavior of certain mesons. Neutrino observatories probe for asymmetries in neutrino and antineutrino behavior. Theoretical physicists explore extensions of the Standard Model, searching for new particles or interactions that could unlock the secrets of the early universe. But so far, the origin of the matter-antimatter imbalance remains a shadowed chapter in the history of the cosmos, one that speaks to a physics not yet fully known. And yet, there is a quiet poetry to it. That we exist at all is a consequence of an ancient and delicate imbalance. That something tipped the scales, ever so slightly, is the reason atoms formed, galaxies coalesced, and eventually consciousness emerged to ask why. The missing antimatter isn't just an absence. It's a reflection of the deep, hidden choices made by the early universe, choices we are only beginning to decode. Chapter 5. The Dark Energy Coincidence. Why now? In the late 1990s, two independent teams of astronomers set out to measure how fast the universe's expansion was slowing down. Based on everything known at the time, they expected to find evidence that the mutual gravity of all matter, galaxies, stars, and dark matter alike, was gradually slowing the cosmic expansion that began with the Big Bang. But the data they returned was both unexpected and unsettling. The expansion of the universe was not slowing, it was accelerating. This discovery transformed modern cosmology. It implied that some unknown form of energy, something not accounted for by matter, radiation, or any known field, was pushing the fabric of space apart. This new phenomenon was given a name: dark energy. It now accounts for roughly 70% of the total energy content of the observable universe, and yet its nature remains almost entirely unknown. Dark energy does not clump or form structures like matter does. It does not seem to interact with light or other particles in any direct way. Its presence is known only through its effects on the geometry and dynamics of the universe. It causes the expansion of space itself to speed up over time, making galaxies recede from each other faster and faster as the cosmic clock ticks forward. At the heart of this phenomenon lies a deeper puzzle, known as the cosmic coincidence problem. It arises from a seemingly simple question: why is dark energy becoming dominant now, of all times in the universe's history? Why does it start to influence the universe in the same epoch that observers like us have emerged to notice it? To understand this question, one must first recognize how the different components of the universe evolve over time. Matter, whether ordinary or dark, becomes less dense as the universe expands. Galaxies grow farther apart, and the average matter density decreases accordingly. Radiation, which also redshifts due to expansion, thins out even faster. But dark energy behaves differently. In the simplest models, its density remains constant. As space expands, the amount of dark energy per unit volume stays the same. Over time, this means that dark energy becomes more important simply because everything else becomes less important. In the early universe, radiation dominated. Later, as the universe cooled and expanded, matter took over. And only relatively recently, within the last few billion years, has dark energy emerged as the dominant factor shaping the universe's large-scale behavior. This is the crux of the coincidence. We live at the brief window in cosmic time when dark energy and matter have roughly equal influence. Not in the past, when dark energy was negligible, and not in the far future, when it will completely dominate. The strangeness of this timing is underscored by how narrow that window truly is. If we imagine the history of the universe as a timeline stretching from the Big Bang to the far future, the era in which dark energy becomes relevant spans only a sliver of cosmic time. This temporal alignment between our epoch of existence and the onset of accelerated expansion seems improbable. It raises the question, is it just a coincidence, or is there a deeper reason behind it? Several possibilities have been proposed to address this coincidence. The most straightforward is that it is a coincidence, a random alignment with no deeper significance. The anthropic argument supports this line of thinking. It suggests that we can only exist in a universe where conditions are suitable for complex structure and life. If dark energy had begun dominating too early, galaxies and stars might never have formed. If it arrived too late, it might have had little observable effect. The fact that we exist now, during the brief period when dark energy is becoming important, is not surprising if observers can only arise in such conditions. In other words, we observe the universe at this time because this is the only time observers like us could emerge. This reasoning is part of the broader anthropic principle, which has been invoked in various areas of cosmology to explain apparent fine-tuning. While the anthropic principle provides a logical consistency, many physicists find it unsatisfying because it does not offer a predictive mechanism. It merely states that we live in a universe compatible with our existence, which is true by definition, but offers little explanatory power. Another approach involves modifying the nature of dark energy itself. In the standard cosmological model, dark energy is modeled as a cosmological constant, a term originally introduced by Einstein to allow for a static universe. In this interpretation, dark energy has a fixed energy density that permeates space, unaffected by expansion or the presence of matter. But this model leads to yet another profound issue, the cosmological constant problem. Quantum field theory predicts that empty space should have an energy associated with it, the so-called vacuum energy. But when physicists calculate the expected value of this vacuum energy using known fields and particles, the result is catastrophically large, more than 100 orders of magnitude greater than what is observed. In contrast, the actual measured value of dark energy is extremely small but non-zero. This discrepancy between theory and observation is one of the largest in all of physics. It suggests that something is very wrong or very incomplete in our current understanding of vacuum energy and gravity. In response, some theorists have proposed that dark energy might not be constant at all. Instead, it could be a dynamic field, a slowly evolving form of energy, sometimes referred to as quintessence. In such models, the dark energy density changes over time, perhaps increasing or decreasing according to the dynamics of the field. This opens the door to new ways of addressing the coincidence problem. If dark energy is evolving, then perhaps its rise to dominance now is the result of internal dynamics rather than pure chance. Other speculative ideas include interactions between dark energy and dark matter, or the possibility that the apparent acceleration is a result of inhomogeneities in space-time itself, that we may be living in a local region of space that expands differently than the universe at large. While none of these models are yet confirmed, they reflect an ongoing effort to go beyond the standard picture and find a deeper explanation for the timing of dark energy's dominance. Adding to the mystery is the long-term consequence of dark energy's accelerating influence. If its density remains constant, the universe will continue to expand forever, growing colder and more dilute as time progresses. Stars will eventually burn out, galaxies will recede beyond visibility, and the cosmos will approach a state of maximum entropy, a so-called heat death, where energy is spread thinly and no thermodynamic work is possible. This lonely fate lies in stark contrast to the dynamic universe we now inhabit. The coincidence problem, then, is not just about timing. It also sharpens the contrast between the universe's past and its eventual future. We live at the cusp, a transitional epoch when stars still burn, galaxies still form, and the expansion is just beginning to accelerate in earnest. Future observers, living trillions of years from now, may find a very different sky, empty, quiet, and dominated by dark energy. Without the light of distant galaxies, they may never even realize that the universe was once filled with visible structure. Cosmology, as we know it, would become impossible. This observation lends the coincidence problem a philosophical dimension. It suggests that we live not just at a special place in space, but at a special time in cosmic history, one of the few windows during which the nature of the universe can be observed and understood. We arrived by chance or by necessity at the precise moment when the ingredients of the cosmos are balanced in a way that makes them both visible and meaningful. The coincidence of dark energy's timing invites us to consider the limits of our perspective. Are we observing the universe in a unique moment, or are we misinterpreting a larger picture that we cannot yet see? Is there a deeper symmetry, a principle, or a structure that will one day make this timing seem inevitable rather than coincidental? These are not idle questions. They touch on the very foundations of cosmology, physics, and even consciousness. Dark energy remains one of the great frontiers of science, a silent, invisible presence that shapes the fate of everything. It defies easy explanation and resists our best efforts to categorize it. Its emergence as the dominant force in the universe, just as intelligent observers appear on a small rocky planet around a yellow star, is either the greatest coincidence we've yet discovered, or the faint outline of something deeper, waiting to be revealed. Chapter 6. Spinning Galaxies That Should Fall Apart. The Galaxy Rotation Problem. When we gaze into the night sky, we see galaxies as immense, glowing spirals, vast collections of stars, gas, and dust held together in graceful rotation. Through the lens of a telescope, these galaxies reveal their structure. Dense, brilliant cores surrounded by sweeping arms that coil outward like cosmic whirlpools. These galaxies spin, and their rotation is one of the most important clues we have about how matter is distributed in the universe. Yet this very motion presents one of the most enduring and foundational problems in astrophysics: the galaxy rotation problem. The issue is straightforward in appearance, but profound in consequence. Based on the laws of gravity and the mass we can see in galaxies, they should not be able to hold themselves together. They rotate too quickly for their visible matter to account for the gravitational pull required to keep their stars from flying off into space. The problem emerged clearly in the 1970s, when astronomers began making detailed measurements of how stars and gas orbit within spiral galaxies. These measurements produced what are known as rotation curves, plots showing how orbital velocity changes with distance from the galactic center. In classical mechanics, one would expect orbital speeds to decrease with distance from the center of mass, much like how planets in the solar system move more slowly the farther they are from the sun. This is a direct result of Newton's laws of motion and gravitation. The gravitational force weakens with distance, so the orbital velocity should taper off in a predictable way. However, when astronomers such as Vera Rubin and Kent Ford measured the actual velocities of stars and interstellar gas in galaxies like Andromeda, they found something extraordinary. The velocities did not decrease with distance. Instead, the rotation curves remained flat, or even rose slightly, far beyond the regions where most of the visible mass was concentrated. This meant that stars in the outer parts of galaxies were moving much faster than they should be if only the visible mass were exerting gravitational influence. According to Newtonian physics and general relativity, this should not happen. At those speeds, stars in the outer regions of galaxies should be flung into intergalactic space. The galaxies should unravel and disperse. But they don't. Galaxies remain stable, rotating systems with coherent structure over billions of years. The clear implication is that there must be additional mass providing the necessary gravitational glue, mass that we cannot see. This unseen mass has come to be known as dark matter, and the rotation problem is one of the strongest observational arguments for its existence. Dark matter, as currently understood, is a form of matter that does not emit, absorb, or reflect light. It does not interact with electromagnetic radiation in any meaningful way, making it invisible to telescopes. Yet it exerts gravitational force, and that force appears to dominate the dynamics of galaxies and galaxy clusters. The prevailing model suggests that every galaxy is embedded within a dark matter halo, a roughly spherical cloud of invisible mass that extends far beyond the visible boundaries of the galaxy. The visible disk of stars is just the luminous tip of a much larger, more massive structure. This halo is what holds the galaxy together, ensuring that the high rotational velocities observed in the outskirts are consistent with gravitational theory. Dark matter not only explains galaxy rotation curves, but also helps make sense of other cosmic phenomena, such as the behavior of galaxy clusters, the gravitational lensing of distant light, and the patterns observed in the cosmic microwave background. When simulations of galaxy formation include dark matter, they produce structures that closely resemble the large-scale filamentary web of galaxies we observe across the universe. Without dark matter, these simulations fail to reproduce the correct cosmic structure. Despite this success, we still do not know what dark matter actually is. Numerous experiments have been conducted to try to detect it directly, using highly sensitive detectors buried deep underground or placed in space. These experiments look for rare interactions between dark matter particles and ordinary matter, but so far, no definitive detections have been made. Candidates for dark matter particles include weakly interacting massive particles, or WIMPs, axions, and sterile neutrinos, among others. Each of these theoretical particles arises from different extensions of the standard model of particle physics, but none have been observed. This lack of direct detection has led some physicists to consider alternative explanations. One class of theories suggests that perhaps the laws of gravity themselves need modification. These modified gravity theories attempt to explain galaxy rotation without invoking dark matter by altering how gravity behaves at large distances or low accelerations. One such proposal is called modified Newtonian dynamics, or MOND, which introduces a new fundamental acceleration scale below which Newton's laws are adjusted. MOND has had some success in explaining galaxy rotation curves without invoking dark matter, especially in small galaxies with low surface brightness. However, it struggles to account for other phenomena, such as gravitational lensing or the behavior of galaxy clusters, where the discrepancy between visible mass and gravitational effects is even more pronounced. Modified gravity models remain intriguing, but the broader weight of evidence still strongly favors the existence of dark matter. Another line of investigation considers whether our assumptions about mass distribution might be incomplete. Perhaps there's more ordinary matter, in the form of faint stars, black holes, cold gas, or other compact objects than we can currently detect. However, detailed surveys and models have shown that these so-called dark baryons cannot account for the full discrepancy. The missing mass is too large and its gravitational influence too widespread to be explained this way. Whatever dark matter is, it appears to be something fundamentally different from ordinary matter. The galaxy rotation problem is not a minor anomaly. It is a foundational issue that touches nearly every area of astrophysics and cosmology. The fact that stars orbit far too quickly in the outer regions of galaxies has reshaped our understanding of the universe. It has revealed that what we can see is only a fraction of what exists. The matter that makes up stars, planets, gas clouds, and even us is only about 5% of the total mass-energy content of the cosmos. The rest is dark, unseen, unidentified, and still poorly understood. In this way, galaxy rotation curves are more than just technical data. They are a direct message from the structure of the universe. They tell us that the cosmos is deeper than it appears, that beneath the visible lies a hidden architecture of gravitational scaffolding that holds everything together. And this message is not confined to spiral galaxies. Elliptical galaxies, too, show signs of dark matter, though their structure makes rotation harder to measure directly. Galaxy clusters, the largest bound systems in the universe, show even more dramatic evidence for unseen mass. The famous bullet cluster, in particular, has become an iconic example. In this system, two galaxy clusters have collided and passed through one another. The visible matter, primarily hot gas, has interacted and slowed down, but the gravitational mass, traced through gravitational lensing, has continued ahead. This separation provides strong empirical evidence for dark matter as a substance distinct from normal matter. The implications are profound. If dark matter is real, then the universe is dominated by a form of matter that we have never directly seen or touched. Our solar system, our planet, and even our bodies may be passing through invisible seas of dark matter every moment, entirely unaware. It surrounds galaxies, binds clusters, and shapes the cosmic web. And yet we only know it by the way it tugs at stars. And if it is not real, if the rotation problem turns out to be a signal that gravity itself behaves differently at galactic scales, then our understanding of one of the most fundamental forces of nature will need to be rewritten. Either way, the question of why galaxies hold together is a doorway to deeper truths about the nature of the cosmos. There's a quiet poetry in this too, that the stars, those distant ancient beacons, are moving too fast for their own good and yet remain in place, orbit after orbit, century after century. Something unseen is keeping them tethered, something silent, massive, and invisible. And perhaps, just perhaps, it is this same mystery that keeps our own world stitched into the greater structure of the universe, a reminder that what holds us together is not always what we can see. Chapter 7. Conflicting Measures of Expansion. The Hubble Tension. The universe is expanding. This realization reshaped modern science in the 20th century and remains one of the most firmly established facts in cosmology. The galaxies are not flying apart through a pre-existing void. Rather, space itself is stretching, carrying matter with it. This expansion is quantified by a single number, the Hubble constant. It tells us how fast the universe is growing in units that reflect the velocity per unit distance. For example, how many kilometers per second two galaxies move apart for every megaparsec that separates them. But as instruments became more sensitive and methods more precise, something unexpected emerged. Two of our best approaches to measuring the expansion rate yield significantly different results, and not by a trivial amount. This mismatch is now known as the Hubble tension, and it has grown from a minor inconsistency into one of the central challenges in cosmology. The universe seems to be telling two different stories about how fast it's expanding, one written in its infancy and one whispered in the present. To understand why this matters, we have to explore how we measure the expansion rate and how our methods evolved over time. In the early 20th century, Edwin Hubble showed that galaxies appear to recede from us in proportion to their distance. At the time, distances were hard to determine, and the first estimates of the Hubble constant were off by a factor of 10. Over time, astronomers refined distance measurement techniques, starting with Cepheid variables, pulsating stars whose intrinsic brightness correlates with their pulse period. By comparing their apparent brightness to their true luminosity, astronomers could infer distance, calibrating the cosmic distance ladder. Later, the discovery of Type Ia supernovae provided a second rung on this ladder. These cataclysmic explosions of white dwarf stars have a consistent peak brightness that makes them visible across vast distances, even in galaxies far beyond the reach of Cepheids. Combining these tools allowed astronomers to measure how fast the universe is expanding today, yielding a value of about 73 kilometers per second per megaparsec. But there's another, entirely independent method, one that doesn't rely on stars or supernovae, but on the early universe itself. The cosmic microwave background, CMB, is a fossil light, a thermal echo of the universe when it was less than 400,000 years old. It captures the moment when matter and radiation decoupled, allowing photons to travel freely through space. Embedded in its faint glow are tiny fluctuations in temperature and density, patterns shaped by the laws of physics in the early cosmos. By analyzing these patterns with the standard model of cosmology, known as lambda-CDM, scientists can extrapolate forward and calculate how fast the universe should be expanding today. This method consistently gives a lower value, about 67 kilometers per second per megaparsec. That's a substantial difference from the local measurements, and it's not going away. As each measurement technique has improved, the discrepancy has grown sharper. The statistical uncertainty has shrunk, but the gap has not. Today, the difference between the early and late universe values exceeds the level of what could be dismissed as random error. It's not a mismatch in method or equipment. It's a message. Initially, some hoped the discrepancy would disappear with better calibration. Perhaps dust in host galaxies was dimming Cepheids more than expected. Maybe assumptions about metallicity or intrinsic scatter in supernova brightness were skewing results. But subsequent refinements, including using alternative standard candles like the tip of the red giant branch, continue to support the higher local value. Meanwhile, the CMB-derived value remains robust. It's not based on one isolated measurement, but on a coherent suite of cosmological parameters. The lambda-CDM model, though simple, fits the early universe data exquisitely well. Its predictions match the shape of the power spectrum, the observed ratios of hydrogen and helium, and the large-scale distribution of galaxies. This success makes any suggested modifications difficult. Any change that resolves the Hubble tension must also preserve everything else that lambda CDM gets right. This puts cosmologists in a rare position, trapped between two measurements they trust and a model that performs beautifully, except where it doesn't. Could this be the fault line where new physics will emerge? One compelling idea is that the universe contained an additional component of energy in its early stages, early dark energy, that briefly accelerated expansion before fading away. This would shrink the scale imprinted on the CMB, changing our interpretation of its angular size and allowing the extrapolated Hubble constant to shift upward, aligning with local measurements. Other models modify the properties of neutrinos, hypothesizing extra types, different masses, or interactions that subtly alter how energy and pressure evolve in the early universe. Another approach involves interactions between dark matter and dark energy, two components that currently seem not to speak to each other. If they did interact, even weakly, it could leave a small but cumulative imprint on the universe's expansion history. There's also the possibility that gravity itself changes on large scales. While general relativity is extraordinarily successful in the solar system, and with black holes, we cannot directly test its full machinery on cosmological scales. Some theorists propose extensions to Einstein's equations, subtle tweaks that could alter expansion without violating local physics. And then there are entirely new frameworks, ideas that posit that the current tension is a shadow cast by a more fundamental restructuring of our cosmological assumptions. These include cyclic models, variable vacuum energy, or multiverse scenarios in which different regions of the universe evolve under slightly different rules. Amid these proposals, a third path is gaining attention: standard sirens. These are not candles of light, but ripples in space-time. When two neutron stars or black holes merge, they emit gravitational waves whose waveform encodes distance information. If such an event also produces light, a so-called kilonova, astronomers can match the gravitational signal to a host galaxy, measure its redshift, and calculate the Hubble constant. These gravitational wave events are rare but powerful, offering a completely independent probe of cosmic expansion. As more gravitational wave observatories come online and detections grow, standard sirens could play a pivotal role in resolving the tension, either confirming the discrepancy or revealing flaws in existing methods. They could also help identify whether the tension is evolving with redshift, indicating that the expansion rate is changing in a non-trivial way over cosmic time. The Hubble tension, while highly technical, opens up a philosophical conversation about the nature of science at the edge of knowledge. It illustrates that even our most confident models are subject to revision, not because they are wrong, but because reality may be more complex than the model can express. It reflects how progress is often born not from clarity, but from contradiction. Historically, some of physics' greatest breakthroughs began as persistent anomalies. The ultraviolet catastrophe pointed toward quantum mechanics. The orbit of Mercury hinted at relativity. The uniformity of the cosmic microwave background led to inflation theory. The Hubble tension, quiet as it is, may be another thread pulling us toward a deeper understanding of the universe. But even if it isn't, even if the tension is eventually traced to an overlooked calibration error or an unrecognized systematic bias, its impact will remain. It has sparked new lines of inquiry, forged new collaborations, and reminded scientists and the public alike that the universe is not a solved puzzle. It is still unfolding, and we are still learning how to read it. It's remarkable that we've reached a point where we can argue over such fine details. a difference of a few kilometers per second per megaparsec in a cosmos over 90 billion light-years across. But those few kilometers matter. They represent the boundary between what fits and what doesn't, between theory and observation, between what we know and what we are just beginning to discover. And perhaps that's the most inspiring part, that in the tension between numbers, in the small gap between two lines on a graph, we find not confusion, but potential. Not failure, but the next question. A quiet whisper from the fabric of the cosmos, reminding us that even the most familiar truths still hold surprises, and that the universe, in its expansion, still has space for wonder. Chapter 8. A strange pattern in the sky, the axis of evil. When we look at the night sky, we see a cosmos that appears, at first glance, remarkably uniform. The stars seem randomly scattered, galaxies evenly dispersed at large scales, and the universe from every direction appears largely the same. This principle, known as isotropy, is foundational in cosmology. It's embedded in the very structure of the standard model of the universe. The assumption that the cosmos has no special direction has allowed physicists to model it with elegant simplicity. Yet buried within the deepest image of the universe, the cosmic microwave background, there may be something unexpected, a subtle, large-scale pattern, one that shouldn't be there at all. It's not a structure in space, like a galaxy or a void, but rather an alignment in temperature fluctuations, and its orientation points roughly in the direction of our solar system's motion, as if the universe had drawn a faint line across its own face. This anomaly has been dubbed the axis of evil, a name both dramatic and oddly fitting, given how much it challenges our understanding of the cosmos. The cosmic microwave background, the afterglow of the Big Bang, is a nearly uniform sea of radiation, only about 2.7 degrees above absolute zero. It varies by less than 100,000th of a degree from place to place, but those tiny variations are everything. They encode the seeds of all structure in the universe. Galaxies, stars, and eventually life itself trace their origin to these minuscule ripples in temperature and density. When astronomers first mapped the microwave background with high resolution, they expected a chaotic-looking distribution of hot and cold spots. What they found instead was a peculiar asymmetry. The largest scale fluctuations, those spanning huge swaths of the sky, didn't match the random, statistically uniform pattern predicted by the standard cosmological model. Instead, they appeared aligned. The quadrupole and octupole moments of the temperature fluctuations, which represent the broadest angular structures in the sky, seem to be pointing in a similar direction. This orientation roughly corresponds with the plane of the solar system, the ecliptic. The odds of such alignment happening by chance are low, though not vanishingly so. Some calculations place the probability around 1 in 100 or even lower, depending on how you quantify the alignment. That alone wouldn't necessarily be cause for alarm. Low probability events do occur. But what makes the axis of evil so unnerving is its persistence. The same pattern has been observed in multiple missions, with different detectors, different scanning methods, and different systematic error corrections. Initially, astronomers suspected it might be contamination, foreground radiation from the Milky Way, solar system dust, or instrumental noise. But even after applying complex masks to remove galactic emissions and performing independent reconstructions, the alignment remained. This resilience has forced cosmologists to consider a more unsettling possibility, that the universe itself might not be entirely isotropic after all. If true, this would upend a central pillar of modern cosmology. The cosmological principle that the universe is homogeneous and isotropic at large scales underpins nearly every theoretical model we have. If there's a preferred direction in space, it would mean the universe has a kind of axis, a cosmic asymmetry not accounted for by the Big Bang as we currently understand it. There are theoretical attempts to explain it. Some posit that inflation, the ultra-rapid expansion in the early universe, might not have been perfectly uniform. A slightly anisotropic phase of inflation could imprint a directional signature into the fabric of space-time, one that would then be frozen into the cosmic microwave background. Others explore the possibility of large-scale topological features in the universe, that space itself may be shaped or looped in a way that favors certain directions over others. More speculative models suggest that what we perceive as the axis of evil could be a projection of deeper, more hidden aspects of the cosmos. Some theories rooted in string theory propose that extra dimensions might influence the geometry of the universe in subtle ways. Others speculate about interactions with regions beyond our visible universe, a kind of cosmic bruising from neighboring inflationary bubbles in a multiverse scenario. There's also the possibility that our own observational framework is flawed, that we're misinterpreting statistical flukes as patterns. After all, humans are remarkably adept at seeing alignments and symmetries, even in noise. The very name axis of evil reflects this tendency, projecting a narrative onto data that may, in the end, be innocent of any wrongdoing. Still, the fact that the alignment correlates with the solar system's orientation is particularly troubling. It raises the possibility that some unknown local effect, something related to our motion, our instruments, or even our data processing, might be biasing our observations. Perhaps there is an error embedded not in the universe, but in the way we look at it. To test this, new observations are being planned. Future missions with more advanced detectors and scanning strategies may be able to isolate the large-scale modes of the cosmic microwave background with even higher precision. Polarization maps of the microwave background, which are less susceptible to some forms of contamination, might offer a cleaner look at these anomalies. If the alignment persists there too, the case for its cosmological origin will grow stronger. Interestingly, this isn't the only large-scale asymmetry observed. Some researchers have noted hemispherical power asymmetries, differences in fluctuation strength between one side of the sky and the other. Others have observed anomalously cold or hot spots that defy statistical expectations. While each of these anomalies on its own may not be compelling, together they hint at a deeper, more intricate structure to the cosmos. In some ways, this situation is reminiscent of earlier scientific puzzles. For decades, astronomers noticed tiny deviations in the orbit of Mercury that Newton's laws couldn't explain. It wasn't until Einstein's theory of general relativity came along that the discrepancy was resolved. Similarly, the cosmic background itself, once dismissed as theoretical noise, became the linchpin of Big Bang cosmology. It's not unprecedented that persistent outliers lead to paradigm shifts. The axis of evil may follow that same trajectory. There's also a historical curiosity worth noting. When early 20th century astronomers like Edwin Hubble began mapping galaxies, they initially assumed the universe was uniformly filled. But they quickly found that galaxy clusters, voids, and filaments made the cosmos far more structured than expected. Each time we've assumed uniformity, reality has found a way to surprise us with texture. The axis of evil may be another lesson in that long history, a subtle ripple reminding us that simplicity is not the same as completeness. Some scientists urge caution. It's tempting to overinterpret small anomalies, especially when they challenge foundational assumptions. Statistical flukes are not only possible, they're inevitable in large datasets. The more one searches for patterns, the more one is likely to find coincidences. This is sometimes referred to as the look elsewhere effect. The idea that if you check enough corners, something strange will eventually pop up. And yet, the axis of evil remains a lingering whisper. It doesn't shout. It doesn't declare a crisis. It simply refuses to disappear. It forces cosmologists to confront the uncomfortable possibility that the universe might not be as blandly symmetric as we hoped. Historically, such anomalies have been the seeds of revolutions. The precession of Mercury's orbit didn't make Newtonian physics wrong, but it did make general relativity necessary. The odd glow in the microwave spectrum didn't make radio noise, it revealed the Big Bang. Perhaps this pattern in the sky is another such seed, waiting for the right theory to take root. Even if the axis of evil turns out to be nothing, a phantom born of chance and imperfection, its impact on science is real. It reminds us to question assumptions, to examine the scaffolding of our models, and to remain open to the strange. In the end, we are creatures looking up from a tiny rock, trying to read a message written across the sky. Most of that message appears clear: expansion, structure, radiation, gravity. But in one faint line, one quiet asymmetry, the message becomes cryptic. Is it a flaw in the ink, or a hint that the message is deeper than we knew? In that possibility lies the quiet thrill of science. That even now, in an age of precision instruments and elegant equations, the universe can still surprise us, not with noise, but with the soft echo of a pattern we can't explain. Chapter 9, where physics breaks down, the black hole singularity. There are places in the cosmos where our most trusted equations collapse into silence. Not because we don't have enough data, or because something is missing from our telescopes, but because the very structure of reality, as described by the language of physics, refuses to go further. These places are known as singularities, and nowhere are they more striking than in the hearts of black holes. Black holes, predicted by Einstein's general theory of relativity, are regions of space-time so severely curved by mass that nothing, not even light, can escape. They are not hypothetical oddities anymore. They are real, measurable, and abundant. We have detected their gravitational waves as they collide, observed their shadows through coordinated global telescopes, and mapped their effects on nearby stars. But while the exterior of a black hole can be explored through indirect means, its interior remains a sealed mystery. And at its center, if our current understanding is to be trusted, lies a singularity. A singularity, in the language of general relativity, is a point where certain physical quantities become infinite. Density, for instance, climbs without bound. The curvature of space-time becomes so extreme that it can no longer be described. This isn't just a mathematical oddity, it signals a catastrophic breakdown in our ability to model reality. And while singularities are predicted by Einstein's equations, the fact that those same equations fail to describe what happens at such extremes means we are staring at the edge of modern physics. Let's take a moment to trace how this idea emerged. In the early 20th century, Karl Schwarzschild discovered a solution to Einstein's field equations that describe the gravitational field outside a spherical, non-rotating mass. This solution revealed a critical radius, now known as the Schwarzschild radius, where the escape velocity equals the speed of light. Any mass compressed within that radius forms a black hole. But deeper within, at the very center, the equations predicted an unresolved infinity. As understanding advanced, this central singularity became more than just a quirk. It became inevitable under conditions of gravitational collapse. Stephen Hawking and Roger Penrose formalized this inevitability through their singularity theorems in the 1960s and 70s. These theorems demonstrated that if general relativity holds true, and if certain conditions like energy positivity are met, then singularities must arise in both black holes and in the Big Bang itself. In other words, the universe began with one, and some stars end with one. But here's the tension. Singularities don't make physical sense. An infinite density in a finite volume contradicts our expectations of how matter should behave. The singularity at the core of a black hole isn't just a dense star remnant. It's a location where the very concepts of location and time begin to blur. The rules dissolve, and we are left without predictive power. In ordinary situations, general relativity and quantum mechanics work beautifully, but they describe different domains. General relativity handles the large and the massive. Quantum mechanics governs the tiny and the energetic. Near a singularity, however, both regimes come into play. Gravity is extreme, and quantum effects cannot be ignored. But we do not yet possess a complete theory that unites these frameworks. A quantum theory of gravity, something that does for black holes what quantum mechanics did for atoms, remains elusive. Some candidate theories offer glimpses of progress. Loop quantum gravity proposes that space itself is quantized, that it has a smallest possible unit, the kind of graininess that would prevent infinite compression. String theory suggests that particles are actually vibrating strings in higher dimensional space, which may smooth out singularities into complex but finite geometries. Neither approach has delivered definitive answers yet, nor experimental confirmation. And so the singularity remains, taunting us from behind the veil of the event horizon. Even more baffling is the question of what singularities mean for information. According to quantum theory, information cannot be destroyed, yet black holes seem to erase it. When matter falls into a black hole, its detailed properties, quantum state, composition, arrangement, are lost behind the event horizon. And when the black hole evaporates over time via Hawking radiation, that radiation appears to be random, uncorrelated with what fell in. This leads to the black hole information paradox, one of the deepest mysteries in physics. If the singularity truly destroys information, then one of our two major theories must be wrong. Either general relativity misrepresents what happens inside a black hole, or quantum mechanics is incomplete in the face of extreme gravity. Numerous proposed resolutions have emerged, from holographic principles to the idea of firewalls at the event horizon, but none have been universally accepted. And yet, despite the impossibility of observing the singularity directly, black holes continue to inform and test our theories. The Event Horizon Telescope's image of the supermassive black hole in M87 provided the first visual evidence of an event horizon. While the image didn't reveal the singularity, it gave confidence that general relativity holds even in these extreme regimes, right up to the edge of the unknown. Gravitational wave astronomy has also opened new doors. When two black holes merge, they release ripples in space-time that we can detect on Earth. These waves match general relativity's predictions with extraordinary precision. But what happens at the moment of merger, when two singularities collide, remains hidden. The final object settles into a new black hole, yet the singularities at its core are never directly involved in the process we can measure. They exist behind the curtain, untouchable by current instruments. The question also arises, are singularities real entities in the universe, or are they simply signs that our equations are incomplete? Many physicists lean toward the latter view. In past scientific revolutions, infinities have often signaled the breakdown of old theories, soon to be replaced by better ones. Classical physics predicted infinite radiation at ultraviolet frequencies, the so-called ultraviolet catastrophe, until quantum mechanics resolved it. Perhaps one day singularities will be similarly resolved, but the implications of singularities extend beyond the mathematical. They confront us with the nature of time itself. Inside the event horizon, the direction toward the singularity becomes the direction of time. It is not that something pulls you toward the singularity. It's that you cannot help but move toward it, because all future moments lie there. Once you cross the event horizon, you are no longer in control of where you go. You are simply moving forward in time, and time ends at the singularity. This presents a unique kind of causality violation. If time terminates at the singularity, then the chain of cause and effect ends there too. The predictability of physics, built on the ability to say what will happen next, disappears, and this does not merely affect observers inside black holes. The existence of singularities implies that our universe contains places where the laws of nature, as we know them, are not valid. That changes how we think about the universe as a whole. Some have even speculated that what lies beyond the singularity could be another region of space-time, a wormhole, a baby universe, or a bridge to somewhere else. These are not proven ideas, but they reflect the hunger to make sense of what remains inaccessible. If a singularity is not the end, then perhaps it is a transformation, a region where familiar physics gives way to something new, waiting to be discovered. Ultimately, the singularity is not merely a point of no return. It is a statement about the limitations of current science. It asks whether space-time is truly continuous, whether infinities can exist in nature, and whether the universe itself has boundaries not just in space, but in knowledge. And still, singularities persist in our theories, like silent punctuation marks, ellipses in the story of the universe. They remind us that even as we stretch our understanding to the edge of black holes, some questions remain unanswered, not for lack of trying, but because the answers may require new tools, new ideas, or a new physics altogether. What lies inside a black hole may never be directly observed, but in trying to understand it, we are forced to confront what it means to understand anything at all. The singularity is a mirror held up to science, reflecting not just what we know, but the shape of what we cannot yet grasp. Chapter 10. The Mystery of Existence. Why is there something instead of nothing? Among all the questions that physics, cosmology, and philosophy have dared to ask, none is more profound or more elusive than this. Why is there something rather than nothing? It is a question that lies beyond the edge of observation and beyond the reach of most equations. And yet, it is embedded in every measurement we make. Every photon caught by a telescope, every atom studied in a lab, every star that glows in a distant galaxy, all bear silent witness to the fact that something exists. But nothing in our current understanding fully explains why. At first glance, the question may seem more philosophical than scientific. Physics traditionally concerns itself with describing how the universe behaves, not necessarily why it exists in the first place. Yet the deeper we probe into the foundations of the cosmos, the more inescapable the question becomes. The laws of physics assume the presence of a universe to govern. But where do those laws come from? And why is there a universe at all for them to operate within? Modern cosmology begins with the assumption that the universe exists and evolves. The Big Bang model describes a hot, dense origin of space and time, expanding outward into the cosmos we observe today. But even if this model is correct and the evidence strongly supports it, it only tells us what happened after time began. It does not explain why time began or what, if anything, preceded it. Nor does it address why the vacuum of space, which seems so close to nothing, is still a dynamic, structured entity. Physicists often attempt to sidestep the issue by pointing out that quantum mechanics allows for something to emerge from nothing. In particular, quantum field theory predicts that even a vacuum, a region devoid of matter and classical energy, is never truly empty. Instead, it teems with fluctuations. Virtual particles emerge and vanish, fields ripple momentarily before fading, and probabilities swirl beneath the surface. From this perspective, nothing is not truly nothing. It is a seething sea of potential shaped by the underlying quantum structure of reality. Some theorists propose a theory that the entire universe may have emerged as a quantum fluctuation, a spontaneous blip in an otherwise featureless background. In such scenarios, the total energy of the universe may be exactly zero, the positive energy of matter and radiation perfectly balanced by the negative energy of gravity. If true, this balance would mean the universe required no net energy to exist, just a spark of instability in a pre-existing vacuum. But even then, we are left with a new mystery. Why is the vacuum there at all? What established the laws that allow such a fluctuation? Attempts to push the question further often invoke the concept of a multiverse. Perhaps what we call the universe is just one bubble in a larger reality, one of infinitely many domains with varying physical laws. In that case, our universe exists not because it was chosen or created, but simply because in an infinite set of possibilities, even extremely unlikely configurations must eventually occur. This idea sidesteps the need for a specific origin by making every possible origin inevitable somewhere. But again, it raises a deeper concern. What framework allows the multiverse to exist? What generates this infinity of worlds? Another approach comes from the realm of mathematics. Some philosophers and physicists speculate that reality itself may be a mathematical structure. If every consistent mathematical structure exists in some form, then one of them might correspond to a universe like ours. This radical form of Platonism suggests that existence arises not from physical causation, but from logical necessity. But even if such a view holds, we are again left wondering why these mathematical truths exist, or why they manifest in the form of a conscious, observable universe. Then there are those who argue that the question is ill-posed, that nothing is not a valid concept. From this perspective, the absence of existence is not a real state of affairs, but a logical abstraction. The universe exists because there is no reason for it not to. Asking why something exists, they say, is akin to asking why the number 3 exists, or why the laws of logic hold. In this view, existence is simply the default, but for many, this answer feels unsatisfying, as it replaces the question with a redefinition rather than a resolution. Historically, the question of why anything exists at all has also been framed in theological terms. For centuries, thinkers from various traditions proposed that the universe was created by a necessary being, an entity whose nature requires existence and whose will sustains everything else. While such arguments lie outside the scope of physical science, they highlight the depth of the mystery. Even the notion of divine creation shifts the question one step back. Why should such a being exist? In physics, one might expect that the laws of nature would point to an inevitable emergence of structure from a more fundamental symmetry. But in many models, the symmetry is broken arbitrarily. Constants of nature, such as the strength of gravity or the charge of the electron, appear finely tuned for the existence of complex matter. This fine-tuning itself hints at a deeper mechanism, or perhaps at a landscape of universes where all possibilities are realized. But again, each explanation gives rise to further questions. There is also the matter of time. The universe appears to have a finite age, approximately 13.8 billion years. But time itself is part of the structure of the cosmos. If we ask what happened before the Big Bang, we may be asking a meaningless question, because time as we know it may not have existed then. In some cosmological models, the beginning of the universe is not a moment in time, but a boundary, much like the North Pole is not a point you can travel past. But if time itself is emergent, then so too is causality, and our question dissolves into the fabric of an origin without a cause. Still, many physicists continue to explore whether a nothing state could be more than just an abstract idea. Can the laws of physics be formulated in such a way that existence itself arises inevitably from a truly featureless starting point? Could the universe be a kind of mathematical necessity, a self-explaining system with no external source? Or is our existence the product of an accident, an unpredictable, spontaneous event with no deeper explanation? This leads to a humbling realization. The very framework of science may not be equipped to answer questions of ultimate origin. Science excels at describing relationships, behaviors, patterns. It shows how things evolve from previous states, how systems interact, how energy is conserved or transformed. But it may not, in its current form, be capable of telling us why there is anything at all to describe in the first place. In recent decades, some physicists have acknowledged this openly. The question of existence may forever remain at the boundary between science and metaphysics, not because it is unimportant, but because it transcends the tools we currently possess. It may be that new physics, new mathematics, or entirely new conceptual frameworks will be needed to approach the mystery. And yet, the mystery remains intimately present. Every measurement we make, every theory we test, every particle we detect is a reminder that the universe is here. It did not have to be, and the fact that it is, while unaccounted for, is perhaps the most startling scientific fact of all. We are accustomed to thinking about the cosmos in terms of mechanisms, how galaxies form, how stars die, how particles interact. But behind every mechanism lies a more basic truth, that there is a stage on which they unfold, a space, a time, a field of possibility. Why does that stage exist? In the absence of a definitive answer, we are left with a moment of pause. To look out into the night sky and see light from stars billions of years old is to encounter not just the immensity of the universe, but the sheer fact of its being. That there is anything at all, not just stars and galaxies, but laws and patterns, observers and questions, is a fact that continues to resist explanation. It is easy to become accustomed to existence, to take the presence of the universe for granted. But behind every scientific achievement, behind every discovery, there lies this quiet astonishment. The universe exists, and we are here to witness it. And in that, perhaps, lies the most profound mystery of all. And so, we drift back from the edge of knowledge, from singularities and strange alignments, to the very mystery of why anything exists at all. If you're still awake and your curiosity is still glowing, another journey awaits you in the next video. But if your eyes are already heavy, then sleep well, my friend, and may your dreams float gently among the stars.